Good afternoon. My name is Kurt Langlotz. I'm the director of the Center for Artificial Intelligence in Medicine and Imaging here at Stanford. And this is the Stanford AIMI Center Invited Lecture Series. In just a minute, I'll be introducing our speaker. Wanted to let you know that Akshay Chowdhury, an AIMI Center Associated Faculty Member and Executive Committee Member, will be moderating the Q&A after this session. So save up your questions or put them in the Q&A and we can discuss them at the end. So I'm delighted today to be able to introduce ZIAD OBERMEYER, who's done groundbreaking work to reveal bias in clinical algorithms and in many other areas. He did his training, undergrad training at Harvard, magna cum laude, got a master's MPhil from Cambridge in the history of science, did his medical training at Harvard, where he worked for Atul Gawande's Ariadne Labs, and also for the Harvard Initiative for Global Health. He did his clinical training in emergency medicine at the Brigham and Women's Hospital, and then joined the faculty there as an assistant professor in emergency medicine. He's won numerous awards, including an NIH Early Independence Award, a prestigious award for exceptional junior scientists, a Young Investigator Award from the Society for Academic Emergency Medicine, and he's been named an emerging leader by the National Academy of Medicine. In 2018, he saw the light and moved here to California, to UC Berkeley, where he is now the Blue Cross of California Distinguished Associate Professor of Health Policy and Management in the School of Public Health. He continues to practice emergency medicine in underserved communities. His research lies at the intersection of machine learning, medicine, and health policy, and he's done some fascinating recent work, which I'm sure he'll talk about today, including some interesting work on racial disparities in the diagnosis of osteoarthritis on radiographs. So we're delighted to have him here talking about dissecting algorithmic bias. ZIAD, take it away.
Thank you so much for that very kind introduction. It's wonderful to be here. It's especially wonderful as a lowly emergency physician presenting to people who did much better in medical school than I did and were able to go into radiology instead. So it's a particular honor. I thought today what I do is maybe set the stage by telling you about algorithms in healthcare broadly, but really work through a couple of case studies. But the overarching theme of a lot of my work, both the positive work on building algorithms and the more critical work on problems in algorithms, starts with the observation that a lot of what we do in healthcare as doctors, as policymakers, as hospital administrators is to target resources to people who need help. And that task is very well suited to algorithmic thinking. So things like risk prediction, what is going to happen to someone? Who do I target now? Even the process of diagnosis, you can think of as something that an algorithm does well. It's taking a complex set of data about a patient and transforming that into predictions on the likelihood that they have a given disease. So there are lots of variations of this. And largely my sense is that it is very good that we're using algorithms in medicine in this way, and they have the potential to be really revolutionary to our practice of medicine, to how we allocate resources in health. But they also have the potential to reproduce and scale up racial bias and other forms of bias. And that is the topic I wanted to talk through today. So today, it's kind of I guess a tale of two algorithms, two case studies on particular algorithms that each have their own particular clinical setting, policy setting. The first is an algorithm that we studied that in a very destructive way scales up the racial bias in the data that it was trained on, and thereby affected decision-making for millions and millions of patients in the US. The second is an algorithm that actually is the opposite. This is the good twin, an algorithm that fights against racial bias. This is a different kind of bias. It's a bias that's built almost into the DNA of the medical knowledge that we learn in medical school. And the common themes that I'll just flag for you before diving in are that in both of these cases, and in a wide variety of cases that we've learned about since, the problem, the mechanism by which bias gets into the algorithm and the way that we fix the problem is by training the algorithm to predict the right target variable, the right label in the parlance of computer science. And another theme that I'll touch on in passing, but would love to talk more about because some of that work is with AIMI and all of the wonderful people that are hosting this symposium today, is how we fix the underlying problems that got us into the mess to begin with. Okay, so with that in mind, I'll just dive right into the first case study, the evil twin. So the setting here is targeting extra help for the complex, chronically ill patients that are at this nexus of high cost, poor fragmented care, ER visits, hospitalizations for emergency problems. And as you all know, and don't need me to tell you, if you look and did a survey across all the major health systems in the US, you'd find that to tackle this problem, almost every single health system has invested in high-risk care management. So most of you will know what this is, but I think of these as basically a VIP program for complex patients with a lot of health needs. So there's a single phone number, and you have a low threshold to call for really anything you need help with, like refilling your prescriptions, getting a next day or same day primary care appointment. Sometimes nurses will even come to your home and do foot checks for diabetic ulcers. So whatever you need, you want to call this number, they will sort it out for you. And they do that so that down the road, they can prevent problems like needing an amputation or an admission for IV antibiotics for your diabetic foot ulcer, to keep you out of the ER with a heart failure exacerbation, because God forbid you have to see me or someone like me in the ER. It's kind of bad care and it's very expensive. But these programs themselves are very expensive. So we can't give all of this extra attention to everyone. And so we need to target the programs to people who need them the most. And that's where algorithms come in. Of course, algorithms are used everywhere in our health system for this. So I'm going to tell you about a particular piece of software that's made by one company. It's one of the biggest ones in the space. So that company estimates that it's used to help make decisions for about 70 million patients every year. If you step back and look at all of the companies, all of the academic groups, all of the nonprofit hospitals that are using similar algorithms, that market estimate is like the majority of the US population every year is being run through one of these algorithms and having part of their decision-making with regard to population health filtered through this algorithmic lens. So the scale of these algorithms is really massive. What all these algorithms do is, the stated goal is today, I want to find patients who tomorrow are going to get sick and have these kind of bad outcomes like ER visits and hospitalizations and exacerbations of their chronic illnesses. The way they do that is they look ahead and they look to see who ends up in the ER and generates costs. So they kind of total up all of the costs from ER visits and hospitalizations and everything else. And they add those up and they train the algorithm to look into the future and predict who is going to have high healthcare costs over the next year. And then we take the high-risk people and we target them for additional resources. So concretely, think of the algorithm as producing some distribution of risk scores. The top 2% in the healthcare system that we worked with to study the algorithm get fast-tracked into this high-risk care management program. The top half, apart from those, approximately gets filtered through the primary care doctor. So that patient, their score, a few other data points gets shown to the primary care doctor, and the PCP has an opportunity to say, oh yeah, that person would benefit or this person wouldn't. And then the bottom are basically just screened out. So they're just put aside. And overall, while the details vary across the systems that we have worked with since our original study, the basic insight is that if you're given an algorithm score, that's going to play a large role in determining how you're treated and your likelihood of getting into these high-risk care management programs. So when we set out to study racial bias or potential racial bias in this algorithm, we first had to really define what that meant. So in the computer science literature and in the policy literature, there's increasing recognition that there are many different reasonable definitions of bias that have been proposed. And not all of them can be simultaneously satisfied because of some basic algebraic constraints. So all of that means that when you're studying bias, you have to really be specific about what you mean by bias. So our definition really comes from this way in which the algorithm is used in this setting, which is to say, okay, two people have the same algorithm score. Those two people are going to be treated the same way. And so those two people should have the same basic health needs that we're using the algorithm to screen for and to allocate this extra help program for health needs. And the color of their skin should not matter. But that is, in fact, not what we found. So I'll show you two graphs that look like this. So I'll just talk through the axes briefly. So the x-axis here is the algorithm score that we've binned into percentiles. The y-axis here is a count. You can think of it like a comorbidity score that gets computed over the next year after the algorithm makes its prediction. So the algorithm makes its prediction today. We look over that entire next year and we see, okay, you had to go into the ER for a emphysema exacerbation, or you got hospitalized for CHF, or you saw your doctor for something else. So we just total all that up, we count them, and then that's a kind of one measure of health. Everything I'll tell you is not specific to this measure of health. We see the same thing with blood pressure, hemoglobin A1C, like kind of lab markers and vital signs and things like that. So that's the y-axis. And the two lines are showing you Black patients on top and white patients on the bottom. And what you can see is that no matter where in this algorithm score distribution you look at on the x-axis, the line for the average outcome of Black patients is higher. So at a given score, two patients, one Black, one white, the Black patient is on average going to have worse health over that next year, even though they're being treated the same by the algorithm. And so, it's a little hard to kind of tell how big this bias is by just looking at this y-axis. But if we just look at that fast track, so this is people in the top 2-3% of the algorithm risk score distribution, and we look at the fraction of that population, the high risk, high priority population that's Black, it's 18%. If we do a simulation where we effectively say, okay, there are some sick Black patients that are not getting into this high-risk group. There are some healthier white patients that are getting into this high-risk group. Let's just swap those people out until the marginal patient is equally healthy. So if we do that simulation exercise, we'd find that an unbiased algorithm would actually have assigned this group to be 47% Black. This is a large amount of bias. So Black patients are dramatically underrepresented relative to their actual health needs in this fast track program, but really wherever you draw the line, that would be true. So a really important question is, where is the algorithm going wrong? How did bias get into this algorithm? And a really important clue to answer that question is where the algorithm is going right. So here on this graph, the x-axis is the same as the algorithm score. But on the y-axis, rather than showing you a measure of patient health, I'm showing you how much those patients cost, the total medical expenditures that those patients generated over the next year. And what you can see is that now the Black patient line and the white patient line are superimposed. So fact number one, cost is going way up in algorithm score. It's doing a very good job of predicting cost. That y-axis is a log scale. In fact, two, it is pretty unbiased for doing that prediction. And in fact, when we do all of our tests and when we look at how the algorithm was actually trained, it was trained to predict total healthcare costs, not a measure of patient health directly. So the algorithm is biased for predicting health, but it is unbiased for predicting cost. How can that be? Well, it's because Black and white patients do not have the same relationship between health and cost. And to simplify this a little bit, you can think of this as the difference between needing healthcare and getting healthcare, and scale that up over lots of different people and places and circumstances. White patients have, on average, better access to healthcare. So when they have a squeezing sensation in their chest, they are going to be more likely to go into the ER and get care for that. Doctors and the healthcare system in general also just treat Black patients differently. And that has also been shown to result in less treatment for Black patients, less referrals for catheterization, conditional on all of the particular circumstances of a case. So for a lot of these reasons, Black patients end up costing less money, even though they are equally unhealthy as white patients. So Black costs are lower, and what that means for the algorithm is that we trained it to be accurate in predicting cost. That was the objective function that the algorithm was given in the training process, but that necessarily implies that the algorithm is going to be biased for predicting health. So in this same data set, so in our data set that we were using, but as we found when we worked with the algorithm, the software developer, later on in our research process, there are many other variables that we could use. So this algorithm was trained on total costs, But that doesn't really get at the core question that the health system and the algorithm maker might have wanted to get at, which is avoidable cost. So insulin costs money. Diabetic toe amputations cost money. Total medical expenditure just kind of conflates those two types of expenses together, even though one is good and we don't want to reduce it, and the other is bad and we do want to reduce it. So we can create measures of avoidable cost. We can also just predict different health measures directly. So we can predict that same measure of comorbidity exacerbation that I showed you. We can predict glycemic control, blood pressure control, all these other things. Now, predicting these health measures requires grappling with a lot of annoying issues. Not everyone has a hemoglobin A1C. Not everyone gets diagnosed. So it's harder, but the benefits are huge. And when we retrain this algorithm in our data set, and when we worked with the algorithm developer to retrain, there are just these huge benefits, not just for equity, not just in terms of getting more non-white patients into the high-risk group and getting them extra help, but it's also just a better fit with the business purpose of the algorithm. The algorithm is supposed to find people who need help. By training it on costs, we're finding people who are already benefiting from lots of medical resources already. So these might be the people who are least likely to need help. So finding these better proxies is a very, very high value activity. And it's also a very practical one because you can often do it in the same data set with the same basic machine learning tools as you used to train your original algorithm that might have been trained on a more biased proxy. So a couple lessons that we took away from this in general. Getting the exact target really matters a lot. Very small distortions, like the difference between cost and health, can get scaled up into large disparities by an algorithm. And that's true even though that initial choice was not unreasonable. Sick people do on average cost more money. That is true for both Black patients and white patients. So this wasn't a malicious choice, it wasn't a dumb choice, but it was a biased choice. And getting that exact target measure, aligning the target with exactly what you want the algorithm to be doing, is a really important thing to do. The second lesson that I'll just kind of go back to a few facts that I told you is that some of the simple heuristics that at least I was used to using about algorithmic bias can be very, very misleading in this setting. The first one is that we often think about an algorithm as biased with respect to the population representation of the group that we're interested in. So I'll tell you a couple of facts about this algorithm in this use case. So in the primary care population that we were working with in our study, Black patients represented 12% of that population. As I mentioned, when we first looked at that high-risk group that the algorithm was prioritizing for care, that population was 18% Black. So you might have looked at this and said, wow, the high-risk group is 50% more Black than the base rate in this population. This looks good. This algorithm looks like it's not biased because it's over-representing Black patients in the high-risk group. But the right number should have been 47%. So using that simple heuristic of just comparing the population that the algorithm is prioritizing to the base rate can be very misleading, and it can understate the extent of bias. It could also overstate it. It's just not the right measure. The right measure is one that really represents what the algorithm is being used for and whom we want to be targeting. The second thing I'll tell you about this algorithm is that the software company that developed it was explicitly worried about racial bias in the algorithm. And so what they did was they took out the race variable and a lot of the other things that might have been correlated with the race variable. Now, we're used to thinking about if there's an explicit racial adjustment in the algorithm, that is suspicious for bias. In this algorithm, there was no race-based adjustment at all. In fact, it was explicitly forbidden to the algorithm. That did not stop the algorithm from being extremely biased. So there's no easy correspondence between the existence of a race-based adjustment and the extent of bias in an algorithm. And there are many counterexamples. There are many examples where removing a race-based adjustment could make an algorithm more biased. So that one-to-one correspondence that at least was in my head when I first started working in this area turns out to be very misleading. The last thing I'll tell you is that bias from this bad proxy training process can be very, very hard to catch. As that graph I showed you suggests, the algorithm was actually doing a great job for predicting cost, and it was doing a great job for both Black and white patients. So had we assessed the algorithm's performance for its stated purpose for predicting cost, we might have concluded that this algorithm was completely unbiased because there was really no difference in realized cost, conditional on the predicted cost for Black and white patients. But that would have been very misleading as well because this algorithm was tremendously biased. So to catch that bias, you can't just run an automated check of calibration or whatever your favorite fairness metric is. You actually need to understand on a deep level what this algorithm is being used for and how the particular objective function of the training label corresponds to that use case, and how that algorithm could be deeply biased, even if it's performing well for the stated purpose of the algorithm. So one of the things that we were very committed to in the wake of this research, so we were very lucky and we got a lot of attention for this study. And one of the things we decided to do was to take advantage of all that attention that we got to translate some of the lessons that we'd learned into real impact. So the first thing we did was we started working with a very wide range of health systems, insurance companies, tech companies around the Bay Area and elsewhere, regulators at the state and federal level, to look around for other algorithms that on the simplest level might conflate cost and health. And we found those everywhere. We also found it's worth noting, not just in algorithms that we use in the healthcare system, but at the health policy level writ large. So if you look at the way that $175 billion of COVID relief funding was allocated under the CARES Act, and we have this very short paper in JAMA from last year that shows this, that funding was allocated proportional not to need measures of COVID, but largely based on hospital revenue from the year before the COVID pandemic started. So you can immediately see that the same problem is going to affect this policy. And as we showed in that paper, not only did the funding miss its mark to a large degree, so lots of funding went to places with very little COVID, with very financially healthy hospitals that didn't really need the money, to such an extent that, I don't know if you saw these headlines, but the Hospital Corporation of America and Mayo Clinic and a few other large systems publicly announced that they were giving money back to the government. And you guys probably know this, but hospitals are generally not in the business of giving money back to the federal government. Usually that arrow points one way and not two ways. So not only did the funding miss its mark by many different measures, it also disadvantaged Black counties and hospitals serving Black populations because those are hospitals that had less revenue and less profits and were less financially healthy. So, this bias, this conflation of cost and health is really everywhere in our healthcare system. But we've also found similar mechanisms of bias induced by training an algorithm on a biased label in lots of other places. So some of the follow-up we've been doing is working on algorithms for diabetes prediction, figuring out which patients go to rehab and which ones are safe to go home, even emergency triage, the most widely used algorithm for triaging patients in the emergency department, contains a similar kind of bias. And most importantly, one of the nice things about demonstrating bias by saying, here's the algorithm score, here's what it should be doing, here's the difference between Black and white patients, is that what it should be doing implies a solution. It implies the label that you should be training your algorithm on. And so a big part of this work is actually helping organizations to roll out solutions to this problem. Okay, maybe I'll just pause there. Let me just take a quick look at the Q&A and answer any questions that have come up for that first half. Jeffrey asked whether there are proxies for race that go into the model, and yes, there are. But critically, there were also proxies for race when we retrained the model on different labels and dramatically reduced the bias. So the source of the bias is not coming from the predictor variables. It's coming, as we demonstrate in the paper, from the label on which those predictor variables are trained to predict. Irv is asking, let me just take a second to read it. I see. So is it possible that the problem is not the algorithm, but the problem is the difference in healthcare provider networks that are seeing these patients? So for example, one thing that I could imagine happening is that Black patients in the population that we studied were disproportionately seeing providers that ordered fewer tests that had less resources. And so that bias could come from the difference in providers. So I would actually, 2 points. One is that there's a kind of simple point, which is that we were studying the primary care population of one hospital. This is a large academic hospital. And so the provider networks there was the same hospital. So everyone was kind of like in the ACO of this academic hospital group. And everyone was in a risk-based contract with either government, like Medicare insurance, not Medicaid, Medicare, or private insurance. So I think those differences were kind of minimal in the population that we studied. But I'd say that even if they weren't, that is, I would say, not a confounding factor, but actually part of the problem. So if Black patients go to doctors that are that order fewer tests because they have fewer resources, the algorithm is going to see that, and it's going to conclude that those patients didn't need more tests and didn't need more resources because that's what's in the data. So I'd say that that actually could easily be part of the problem that we're seeing in other settings. And I'd say that that would still be a problem with the algorithm because we trained the algorithm to predict the cost net of all of those factors. Okay, so I'm going to switch gears and now go to our good twin. This is the algorithm that, rather than reinforcing bias, fights against it. So switching gears completely from the policy world to the clinic, to your world in radiology, pain is not evenly distributed in society. So I find these statistics really striking. So there are these surveys that just ask people, over the past few days, how often have you been in severe pain? And you can see that Black and Hispanic patients are twice as likely to be in severe pain as white patients. The similar gradients by income, by education, however you want to look at it. So these are just huge, huge differences in severe pain. If you're like me, you would immediately jump to an obvious explanation, which is like, well, in these populations, lower income, non-white, there are just more things that hurt. So the prevalence of painful conditions could just be higher. And so we'll be kind of talking about osteoarthritis of the knee as our kind of model organism for the purposes of this talk. And as with many other purposes of or causes of pain, knee arthritis does have these same gradients. They're a little bit less stark than the pain gradients. And it turns out that they don't actually explain this story. And the reason we know this is because there are lots of studies in literature that actually explicitly adjust for that factor. And so continuing with the knee arthritis example, we take a bunch of patients who have both pain reports and we have some grading of their knee radiographs. And we can actually just control for the knee radiograph severity and compare the pain scores. And what we find in those exercises is that even when we are taking two patients whose knees look exactly the same on the X-ray, Black patients and low income, low education patients still report more pain conditional on that X-ray appearance. So that's kind of interesting. And the literature has studied this for a long time. And the general way that the literature deals with this and explains this really puzzling finding is if the source of the pain isn't in their knees, if like the knees look the same, then the source of the pain has to be elsewhere. And the source of the pain could be in their heads. And I don't at all mean this in a pejorative sense. There's a lot of very, very solid research that applies the same physical stimulus, for example, to patients who report more or less anxiety, depression, and find that people who are under stress experience more pain from the same physical stimuli. There's a lot of research on how psychosomatic factors might play a role, like depression and anxiety might be manifested, reported as pain. Also, given the enormous burdens that are on poor patients, non-white patients, they might just have less mental bandwidth to cope with pain and deal with it than others who have more resources. We might also find differences in the way that the medical system treats people. So access to pain control, physical therapy, all these things. So all of these things are very plausible, but notice that all these things have one thing in common, which is that they are not in the knee. So we're looking elsewhere for an explanation for why Black patients, for example, report more pain in their knee than others. So just to make this very concrete, let's imagine a patient who's coming in with knee pain and you send them, you're a primary care doctor, you send them for an X-ray. And if we take this literature seriously, what that X-ray is likely to find is that on average, even though the Black patient that you're seeing is going to be reporting severe pain, the radiologist is more likely to look at that X-ray and say, yeah, this actually looks okay, or it looks kind of, mild, mild to moderate, something like that. So the pain that your Black patient is reporting is going to be less reflected in the disease severity that the radiologist is going to come back to you and report. And as a result, you as the primary care doctor or the emergency physician or the orthopedist are going to be more likely to point that patient in different directions for therapies that don't target the knee. Maybe a therapist, maybe an antidepressant, maybe something else. Notice that all of these statements that I've made hinge fundamentally on what we mean by disease severity. So how bad is the disease in someone's knee and how we measure it. And as you all know, the current state of the art looks like this. It is a person looking at a radiograph and grading it according to objective criteria. And the objective criteria, as you know far better than I, are things like the Kellgren-Lawrence scale for measuring the severity of arthritis. And if you go back to the original papers, these were published in the 50s and early 60s. And all of these papers are basically doing variations of studying coal miners in Lancashire, England, comparing them to office workers in Lancashire, England. And in those papers, there's no mention made of the subject's race or the subject's sex because they're all white Lancashire men. And that was, just the way that medical knowledge was generated at that time. But that system is still with us today for looking at X-rays that are from fundamentally different populations. So all of this might lead you to believe that this would be a very good job for an algorithm. After all, human radiologists might be overlooking causes of pain that disadvantaged groups suffer from. And as we all know, humans are approaching or exceeding, algorithms are approaching or exceeding human performance in the interpretation of radiographs. And so we might be optimistic that an algorithm could help. But remember what we typically do in these machine learning papers. We take a bunch of X-rays and we train the algorithm to tell us what the radiologist would have said about that X-ray. So we train the algorithm to match human performance. And occasionally, if we're using majority vote, we can have it exceed the performance of any one human. But the label, the objective function of the algorithm is tell me what the radiologist would say about this X-ray. Tell me what this ophthalmologist would say about this fundus. Tell me what this cardiologist would say about this ECG. So that is exactly what we don't want to do if we suspect that there might be a problem with what the radiologist is seeing, with what the radiologist has learned about arthritis. So what we did was to try to find a better target for prediction. So rather than training the algorithm to look at a bunch of X-rays and spit out, for example, the Kellgren-Lawrence grade that a radiologist would assign to that knee, we trained the algorithm on a different label, which is the patient's report of pain. So finding these data is not straightforward. So it's very, as you all know, it's very easy to find data sets that pair X-rays with what the radiologist said about that X-ray. That is what's sitting on every hospital's PACS system. It is very easy to find. There's no intensive data work involved. It is much, much harder to find data sets that pair X-rays with patient-reported outcomes, with what the patient would have said about that knee. And some people would say rightly that that reflects the fact that hospitals are generally much more interested in what doctors say about patients than about what patients say about patients. But notice that once you have those data, you can use that exact same machine learning playbook and repurpose it to predict something completely different. Input a bunch of knee X-rays, train a very standard convolutional neural net, and output not the radiologist label, but the patient's report of their pain. Now, there's something kind of that sounds like a nuance, but I just want to flag because it's very important. We are not giving the algorithm access to anything apart from the pixels in the knee, and we're asking the algorithm to predict which knee is painful, which knee is the patient going to report pain from. If it can do that, if those predictions aren't garbage, if they're not just random noise, that means that there has to be something in that knee film that is correlated with the pain. So all of the concerns that you might have about like, oh, pain is so subjective. Pain is like a random number generator. It's like what you had for lunch, which side of the bed you woke up on. It's just kind of like what mood you're in. None of those things are in the X-ray. So if the algorithm can predict pain, there's something in the X-ray that's helping that algorithm to predict pain. So here's a very basic kind of statistic about the difference in pain between Black and white patients, just to start us off. This is the KOOS pain score. The max, like no pain is 100 on this somewhat counterintuitive scale. Severe pain is less than 86. So it's kind of like flipped, at least I think of it as flipped. So no pain is 100, severe pain is 86 or under. And this is the difference between black and white patients, just no adjustment for anything. There's an 11-point difference between black and white patients. So black patients are more than half of the way between no pain to severe pain relative to white patients. This is a huge just baseline difference in pain. If we control for the Kellgren-Lawrence grade of the people in the sample, we can explain a little bit of that gap. So black patients, it seems, do have worse arthritis, and that explains 9% of the gap. But if we use the algorithm's prediction, if we adjust for that algorithmic severity measure instead of adjusting for the Kellgren-Lawrence grade, we explain about half of that gap, so 5 times more than the standard measure. Now, Steve has asked a very, very important question, which is, could the algorithm basically be reconstructing race from the images? So I'll just spell out that concern because it's a really important one. Let's say the algorithm wasn't finding anything related to pain in the knee. It was just finding something that correlated with race. So it was able to reconstruct from this algorithm and guess that this patient was black or this patient was white. In the data, it's very clear that black patients have worse pain. So the algorithm could intuit that this patient was having worse pain than this patient, not by finding anything in the knee that was hurting, but just by knowing that that person was black. So the way we deal with that, and I'll kind of come back to that in a second, but just since you asked this great question, in this regression, we can actually control for race directly. So rather than saying, okay, maybe the algorithm is imperfectly reconstructing race from this radiograph, we can just give this regression race and see if that changes the algorithm's explanatory power, and it does not. So the algorithm keeps all of its explanatory power for pain and all of its power for reducing this pain gap, even when we tell it effectively who's black and who's white. So we don't think that that's what's going on, but it's a really important concern. We see similar results for differences between low and high income patients, low and high education patients, although less pronounced than for black patients. So is it reconstructing race or related concerns? Could this actually be reconstructing BMI, diabetes, other things that correlate with pain? We control for all those things directly, and it doesn't really change how much of the patient's pain the algorithm is explaining. So we don't think that's it. We can hold out individual study sites. So this comes from a multi-site NIH longitudinal study. So it doesn't seem like the algorithm is keying into the fact that some patients are more, patients going to this site are reporting more pain than others, and this site has funny looking radiographs. So it doesn't seem to be that. It also doesn't seem to be better weighting or learning features that radiologists know about it already. So we can't explain the algorithm score, even with the very fine-grained subcomponents of the Kellgren-Lawrence score. So the algorithm is finding new signal in these radiographs that aren't at least present in any of the Kellgren-Lawrence grading system, even the very fine-grained subscores. Irv asked a great question about cultural reporting of pain and how that might be different. So again, that would be something that's not in the knee, except to the extent that the algorithm is reconstructing race from the knee film, and we can control for that directly and show that that's not true. So we don't think that this has anything to do with the fact that cultural reporting standards might be different for pain. So I'll just point out that the stakes here are pretty high because a big part of how we think about whether it's in clinical guidelines or just informally in the clinic, how we think about allocating things like knee replacements is based on the severity of disease. And so, in general, surgery goes to people who are in severe pain and also who have severe disease in their knee. We don't want to be replacing the knee of people who are reporting knee pain because they're anxious or because they have poor coping skills. But again, severe according to whom? So we can do a simulation. So we take all the patients in our data set who report severe pain. And then we say, okay, let's simulate who's eligible for surgery. First, by looking at the people with the worst Kellgren-Lawrence grade. And second, by looking at the people with the worst or the most severe algorithmic pain scores. So the algorithmic pain score is just the pain, but predicted from the x-ray. So correlating to something in the knee. If we flip that, if we sub in the algorithm score for the Kellgren-Lawrence grade and use this, in combination with the kind of standard guidelines for surgery or eligibility criteria for surgery, we would double the fraction of Black patients' knees that are eligible for surgery under this rule. And these rules are not like, this isn't a guideline from the academic literature. Many payers actually build these rules into their payment criteria for determining whether or not they'd reimburse surgery. So these rules have real bite. So the converse of that, if you look at severe pain, but ineligible for surgery because the Kellgren-Lawrence grade is too low, that would reduce the number of Black patients whose knees are left in severe pain, but who might have something in their knee, but they're not being deemed eligible for surgery. And that's really important because these are exactly the knees that get prescribed opiates in our sample. Think about it, it's people who have severe pain, but their knee looks okay. So you're like, maybe I'll give them a short course of opiates. That's what happens in these data. And it is just a testament to that misallocation and misdiagnosis of in the knee versus outside the knee problem. So I'll just close and look forward to a discussion on a lot of these things by saying that why would we think that human labels, radiologist interpretation, cardiologist interpretation, ophthalmologist interpretation of images are incomplete? Well, it's because medical knowledge is incomplete. This is not a controversial statement. And the closer that we can get our labels to real outcomes, to learning from nature, rather than learning from the radiologist or the cardiologist, the closer we're going to get to training our algorithms on the true quantity of interest, and the closer we're going to get to the real spirit of what medical discovery has looked like for ages, but boosted with all of the advantages that algorithms can give us for processing high-dimensional data. The problem, of course, is where do you find these data? So where is our ImageNet for medicine? So one of the things that I was very excited to be working with AIMI at Stanford on is our work on what we call Nightingale Open Science. So this is effectively what we're trying to build is a smaller, de-identified, secure, curated version of ImageNet for medicine. We work with health systems to invest in their data infrastructure, to build interesting data sets that are curated around important clinical questions like osteoarthritis, like diagnosing silent myocardial infarction, all of these really important clinical questions that we don't have a handle on clinically right now. And then we take a de-identified subset of those data, we put it up on our cloud platform, and we make it accessible to nonprofit researchers under a very lightweight DUA that looks like Mimic and free of charge. And all of that is supported by, I'd say we have a type for donors. It's kind of tech people who want medicine to be revolutionized the way that their fields were revolutionized by data and by algorithms. And we're very happy to be working with AIMI at Stanford on that work. Getting that right label is really central. It is a huge source of bias, not just in health, but you can think of all the analogies to other fields. So in criminal justice, we're often interested in someone's intrinsic propensity to crime, but we don't measure someone's intrinsic propensity to crime. We measure a variable called arrests or convictions. And we all know that that is not an unbiased readout of someone's propensity to crime. We see it in hiring. We want a good employee, but what is a good employee? Is it one that gets good ratings from their fellow employees? All of these biases that creep into evaluation reports on colleagues, on peers, on superiors, on subordinates are going to come into play. So I think this is, for me at least, a big bet that I'm kind of betting my career on, which is that this is a huge opportunity. There's a ton of technical knowledge, of course, locked in computer science. There's a ton of clinical knowledge that's locked in medicine. There are very few people that are able to be bilingual translators and work at the intersection of those two fields. And I do think it's a new scientific field. And I think that the people here in this audience, I hope, are the future of that field. So let me stop there and would love to have as many questions as we have time for.
Thank you very much, ZIAD. That was a wonderful presentation. And I really love the exposition where you started off by talking about whether or not there's bias in some of our machine learning models. But I think you were able to go far beyond that. And we're simply pointing out that maybe there's this bias in how we perform healthcare, and our ML models are just simply doing and looking at data that we've collected already. So really covering the continuum over there. So thank you very much for that wonderful presentation.
Yeah, I love the way you put it. I think everyone, it's very tempting to blame the algorithm. And luckily algorithms don't have feelings, their feelings can't be hurt. But if you were a feeling algorithm, your feelings might be hurt. Because it's like, dude, I'm just doing that. You told me to do this thing, and now you're angry that I'm biased. You're the one who chose this task. Why are you calling me biased? So
it's great in dissent at the end of the day, in a way. So again, my name is Akshay Chaudhary. For the audience here, I'm one of the associate directors at the AIMI Center, and I'm excited to start this moderation. And I'll just say, I see quite a few questions coming in the Q&A. So definitely please keep that coming. But maybe I can start by continuing the point that you made last, ZIAD, about using machine learning almost as a lens to see what sort of biases exist in our healthcare system. And I was wondering if you might have any comments on risk stratification and risk scoring. So right now we have systems like the hierarchical condition category that drives a lot of reimbursements, a lot of money exchanges hands. I was just wondering if you had any insights as to, based on some of the studies that you performed, are there any sort of changes that we could make to this model, and what could those look like, and maybe even how feasible are those?
Yeah, it's a really great question. And I think that, one thing that I've been interested in for a while that I'll just kind of put out there in case anyone has ideas is that I think that, the way most insurers, but notably Medicare, calculates its reimbursement rates is by looking at what things cost in the data. And then, coming up with some average, coming up with some, sense of the distribution. And, but if we take this result seriously, that conditional on health, Black patients have lower cost, that is weirdly going to be under reimbursing some hospitals and over reimbursing others, just by virtue of using that average cost. So if there's hospitals where there's undiagnosed problems, like undiagnosed mild heart failure, or COPD, that just means you stay in the hospital longer after your surgery, but no one's really done the echo. No one sent you for your pulmonary function test. So that's not, it's not coded on your list of secondary diagnoses. That hospital is going to eat the cost of that patient's undiagnosed sickness, but it's not the hospital's fault. It's the fault of the system that hasn't diagnosed those problems and isn't reimbursing adequately. So I think these biases go very deep. And I'll say that in our study, we certainly did not solve this problem, because what did we use to retrain our algorithm? We used, diagnosed exacerbations of chronic conditions, but we know that that's biased too, because some patients are going to have more access to the healthcare system than others. So I think it's very possible to make progress, but we should be very, very clear that there's a lot more progress to be made. And the real progress is not in some clever way to retrain the algorithm. It's in generating new data that actually accurately represents the diseases that patients have, not just if you're rich and have access to a concierge PCP, but if you're in a poor neighborhood and it's really hard to get your PCP on the line and get an appointment.
And that leads to another great question that's being posed in the chat by Michael Gensheimer, who wanted to get your thoughts on the trade-offs between fairness and accuracy for algorithms. And Michael refers to the ProPublica recidivism study, where the algorithm itself was well calibrated, but then because of some of the underlying racial biases, there were difference in false positives as a function of race.
Yeah, so it's a really important question, and I think I alluded to this, but didn't. I was very breezy about it. So the ProPublica example is the best known example of this result, that there are many reasonable sounding definitions of bias. So one is like, if I say someone has a 20% chance of committing a crime, a white person and a Black person should have a 20% chance of committing a crime. Another definition is like, if I look at, people that the algorithm said was low risk, those people should have the same likelihood of having committed a crime, so there are many, many reasonable sounding things. They are mathematically incompatible, except under very specific conditions that rarely exist in data sets. So all this really emphasizes, I think, the importance of saying, what is the decision that I care about that I'm using the algorithm to inform? Who is the decision maker? What's my objective function as the policymaker that I am trying to optimize with this decision? And we used one that's most closely related to calibration. So I think in Michael's formulation, that would be like accuracy, because it's kind of the same accuracy, but that's not always the right one. So for example, we're working on a problem related to emergency triage. So emergency triage, accuracy might not be the thing that you care about. You might really care about, for example, something more like sensitivity or the false negative rate. If I say someone is low priority but they're having a heart attack, if I say someone's higher priority, the doctor looks at them and they're like, okay, you're low priority, so I've lost nothing. So the fact that the errors are very asymmetric might make you think, oh, actually, I should not just be using accuracy. So it really all depends on the particular use case that the algorithm is being deployed to inform and what the relative costs and benefits are. And that's, I think, why these decontextualized measures of fairness are a good starting point, but you need to combine those with the knowledge of healthcare that people in this audience surely have to choose which one of these incompatible measures you want to use in your particular application.
Yeah, and it really does come down to the choices of labels. We can assign so many different labels from a machine learning perspective, but do those labels really correspond to what is important clinically? And oftentimes there can be a large discordance there. That's a wonderful point. And I love the fact that you brought up mathematics and optimization. And maybe if I put my machine learning hat on, I always try to quantify things. So do you think it's useful to try to quantify biases in one way or the other? With the perspective that if you quantify something, someone will try to minimize it and try to beat state of the art? Or would that lead to some slippery slopes into other worse scenarios, perhaps?
So, it's a really thoughtful question. And I think, here's what I found. I think that if you look in the medical literature on disparities, at some point got stuck in this rut of quantifying the many ways in which Black patients do worse than white patients, poor patients do worse than rich patients. And I think that rut was a rut because there was no, after we started to widely accept this truth, there was no next step besides fixing society. And I think that there was this incompatibility between the people who were showing these really important disparities in medicine and the people who actually had the ability to do something about those disparities, which often were about housing and income and employment. So what I like about working in this particular area is that there's a very tight link between quantifying the bias and fixing the bias. And so what we found in our work with a lot of different actors in the healthcare system is that it's very compelling to say, your algorithm is predicting this. It's under prioritizing Black patients by 20%. How do I know that? Well, because look at this label that is actually closer to the true thing that your algorithm should be predicting. Let's retrain on that label. And then overnight, you have actually improved the way that health system is doing something in a way that is really hard to do in a lot of other places that we really care about bias. So lots of those other problems involve fixing human biases and fixing kind of deeply broken institutions. And I don't know how to do that, but I know how to fix an algorithm, and that can have a huge return overnight.
Yeah, and perhaps for situations like those, as a first step, just understanding what those problems are is so tantamount before trying to solve everything.
Yeah, absolutely.
Maybe right now I'd like to transition to the second part of your talk, which really talked about the osteoarthritis and the knee pain that patients suffered from. And as an osteoarthritis researcher myself, I find that fascinating.
Oh, great.
But maybe I wanted to start off with a question just that talks to the design of the osteoarthritis initiative, which was the data that was used for this study. So the OAI was slightly more enriched for participants who already had osteoarthritis or had some of the risk factors. And I'd be curious to hear your take about, would your conclusions change about trying to apply some of these findings to a broader subset of the population, or would they remain the same?
Yeah, it's a really important question. And I think, correct me if I'm wrong, but my impression was that the way that the OAI enrolled was like this sort of funny set of criteria, which was like people with knee pain, but also people who had arthritis, and also people who were likely to develop arthritis. So it was kind of like I think they were trying to just have a big tent and get a lot of knees in the door, and that's good. And I think it is just an amazing resource that the NIH built that let us do this work. That said, the sampling frame is a little weird. I don't know how that's going to generalize to like a primary care population at a hospital. And so one of the things that we are actually doing with, I don't know if you guys know Judy Gichoya at Emory, She is in our kind of Nightingale Open Science family initiative, and she's actually building that data set that would answer your question. So in the people attending primary care clinics throughout the Emory system, which is an incredibly diverse system socioeconomically and ethnically, what kind of results would we see if we applied this same approach? If we applied our algorithm trained on OAI, if they trained up a new algorithm, if we looked at long-term outcomes. That was like one thing that, in OAI, we didn't have the power to look at like fractures, other kinds of like long-term outcomes that we wanted to look at. And so we're trying to build that out because those questions are so important.
Yeah, that'll absolutely be a very exciting resource because I guess one of the largest problems that we see in osteoarthritis research is the discordance between structural findings and pain findings. Someone could have KL4 knees, but they report no pain. And someone could have perfect joint space narrowing, but they still have a 9 out of 10 pain. So maybe trying to understand those mechanistically could be really important.
Oh,
and perhaps that could be my next question. And I think a couple of people from the Q&A asked that. So now we've been able to build a model that can predict pain from these radiographs. Can we actually use that to build up a better understanding of what the disease is? Because we still don't know the pathophysiological mechanisms. So I was curious if we're able to see anything interesting that we may not know with how we typically interpret radiographs.
Yeah, it's a fantastic question. Just to go back to your previous comment, it's such a deep point about medicine in general and how little we understand about pain. Like, back pain, herniated discs, endometriosis. Like there's everywhere you look, there's this very weak correlation between the things that we see on our imaging studies and the patient's report of pain. And I think that's just a fascinating opportunity. And a lot of the data sets that we're trying to build up on Nightingale try to actually get at different versions of that problem by pairing pain scores with structural imaging kind of thing. So it is a very deep question. Here are some of the things we're trying to do, or that we at least like have thought of to try to build up that knowledge. So one way to do that is that in the OAI data, we actually have MRIs for a subset of patients. So you could imagine actually just, let's take, as a population of interest, patients in whom there's a discordance between the KL grade and the pain report, where the algorithm is getting it right. What's on those MRIs? So kind of correlating that, the difference in score where the algorithm is getting it more right than the KL grade to MRI findings rather than just the radiographs. Another thing we thought of doing was like taking patients with the same KL grade and holding constant a bunch of the subgrade like components, but where the algorithm score was very different, just showing those paired studies to radiologists and asking them, what's different about these two images? To kind of getting them to riff on the image. So we haven't produced anything of value on this, but we've been thinking about it a lot because it's a really, really important question.
Yeah, I think utilizing the wonderful OAI data set in that regard and using some of those MR scans could really help elucidate disease structure more, because I think how we think of OA, it's not a singular disease. There's probably multiple different pathways anyway. So using that additional data may bring out an immune pathway that we may just not know about. So that'll be really interesting.
And I think that highlights just one other thing that we're doing. This is a Nightingale, but in general in our research is linking these things to laboratory studies. So it would be really interesting, for example, to have for all these people ESR and CRP. So maybe there's a tiny subset. So on average, there's no relationship between pain and ESR, but maybe in some subset based on the imaging there is, and those are a different kind of person that need a different kind of care.
Yeah, I think what you're doing with Nightingale is really exciting. Maybe I had a question in that regard. You mentioned that there's this big initiative to try to build new open source medical imaging labeled data sets, but perhaps in the absence of labels, do you see any unsupervised or self-supervised learning strategies that could be useful to parse through the data sets that we have already or data sets that we'll collect in the future to try to, again, understand more biases or build more mechanistic understanding of disease using some of the more up and coming ML techniques?
This is, I'll just say, I've been looking for places that we can use different kinds of unsupervised things or like generative models in different places. And I've never quite found a great use case for them, but I have this deep sense that they're going to be really useful somewhere. I'll just say that there's often this thing where it's, here's the loop that I've gotten stuck in that has been hard to get out of, is you run something unsupervised, it clusters people into 3 groups. How do you know those 3 groups are useful? Oh, look, this group goes on to have this thing. This group goes on to have this thing. It's like, okay, why don't you just predict that thing? Yeah. So the validity of the unsupervised task is now determined by the prediction, but then why not just do the prediction? So that's where I've gotten stuck, but I'm pretty sure there's going to be something there. I just haven't figured it out yet.
And I guess that just goes back to how we started this discussion. We have the methods, we can build the methods, but how meaningful are they at the end of the day? Time will tell. But in any case, we're almost at 4 o'clock. So thank you once again very much for this beautiful presentation and this lovely discussion. And we're really excited with what you're doing in trying to expose some of these biases and really trying to fix them, and everything that you're working on with Nightingale too. It's a wonderful venture. So thank you again. And thank you for our audience for tuning in, and looking forward to interacting with some more of you in the future.
Thank you all so much for having me.
Yeah, absolutely. Bye-bye.